So here we're going to sketch the graph of a rational function, and we're going to try to use our graph to analyze its end behavior. I'll show you also that we actually don't need a graph to do that. So, but let's first focus on the graph. Usually you start by looking at the domain of the function, okay, just to see where you're going to actually sketch it, like on which part of the x-axis. So let's look at the domain. So it's a ratio of two polynomials, so we do not want to divide by 0 anything, so we have to remove -2 from the reals. Okay, now typically for our rational functions, the value that you remove, okay, indicates that when x equals -2, okay, which is which is a vertical line, this is where you might find a vertical asymptote. So this might be a vertical asymptote. So it's those values that make the denominator 0 that are typically candidates for generating a vertical asymptote. So I say might be because there are situations where they're not. Okay, for example, just like think about this case. This is the rational function. So pretty much for any values except -2, this is the same thing as 1. So in fact, you'd have a function that would be 1 all the time, except that at -2 it's just undefined. So this is why I'm saying, like, in some cases you may not have a vertical asymptote for the value that's not part of the domain. But in general, that's going to be the case. Next thing is to better graph this function, especially if you've got a linear term. I strongly recommend trying to do long division. Okay, so there's actually a way of graphing this without what I'm about to do, but we see actually this in calculus. And in fact, we're not going to spend a lot of time in graphing rational functions. You're going to see that in a much better way in calculus. So for us to graph it, we're going to do long division. Okay, so I'm going to divide 3x plus 7 by x plus 2. How can I fit x into 3x? Well, I need to multiply it by 3 to fit it in. So that's 3x plus 6 after multiplying by everything, x plus 2 by 3. I subtract. 7 minus 6 is 1, and it stops here because the degree of 1 is less than x plus 2. So this means what? It means that y equals 3x plus 7 over x plus 2 is 1 plus, it's 3 plus 1 over x plus 2. And having it written down like that, it's going to be easier to see how that's actually a transformation of the toolkit function 1 over x. So I'll let you do that. Think about how this is a transformation of the function 1 over x. Pause and come back. So the 2 here is going to shift 2 to the left, 2 units to the left. And the 3 here will shift 3 up, 3 units up the function 1 over x. So that's all we have to do. So 1 over x looks like this. And then we just have to perform those transformations. So if you shift, let's start with the shift 2 to the left. Okay. And here, the order doesn't matter, but I tend to do I tend to consider this first, because this is the one that's affecting 1 over x. So the plus 2 is affecting 1 over x first. So I'm going to shift 2 to the left, which means that the vertical asymptote, which used to be at 0, is now at -2. So actually you see here that I had a guess that maybe x equals -2 would be a vertical asymptote, and now I've got confirmation that it's going to be an asymptote. So this would be 1 over x plus 2. Y equals 1 over x plus 2. I'm gonna erase it almost immediately because I want to include the shift 3 units up immediately. So in my head, this is what I would see. Oh, this is how the function will look like. But I'm going to need also to shift it up by 3. Okay, so that's also going to shift my horizontal asymptote, which used to be the x-axis. So if I shift it 3 units up, it's the line now y equals 3. Okay. So that means my function is going to look like this now. So I can see there are like some important points. There's an x-intercept. There's also a y-intercept. Okay. If we can, we're going to find what those are. So the y-intercept, maybe that's the easiest. Okay. I just need to calculate what happens when x is 0. When x is 0, y is 7/2, which is 3.5. So this is 0, 7/2. What are the x-intercepts? There's actually only one normally. So let's see that. Let's confirm that I only find one value where y is 0. So it's 3x plus 7 over x plus 2. Now a fraction can only be 0 if the numerator is 0. So that's the same thing as saying that 3x plus 7 is 0. So x is going to be minus 7/3. Okay, which makes sense. I've got a negative value here. So this is negative 7/3, 0. So my x-intercept, maybe I should add it here, minus 7/3, 0. Okay. Got my y-intercept is 0, 7/2. Now finally, we're going to use our graph to, and this is y plus 3. Here we go. We're going to use our graph to analyze the long-term behavior, so or the end behavior of our function. So what happens when x goes to infinity? So when x goes to infinity, what happens to y? Well, we need to look at the end behavior. So this is where we're looking at our function. When x is large, you see y is going to get closer and closer to my horizontal asymptote, y equals to 3. So the y values on the curve are going to get close to the y value on the horizontal line, y equals 3, so it's going to approach 3. And when x goes to minus infinity, now I'm looking at what happens here. And again here, we're going to be approaching 3 again. Okay. So we can graph our function to find our end behaviors, but sometimes it's actually hard to graph those functions. So I'm going to show you like a pretty interesting way of getting the end behavior when you have a rational function. Okay, so when x is large, so when it goes towards plus or minus infinity, it doesn't matter. If we look at 3x plus 7 over x plus 2, which is our y, right? If you look at the numerator is 3x plus 7. Imagine x is like a million. Okay, if you replace x by a million, you get 3 million plus 7. So you do realize that 7 is almost insignificant proportionally to 3x. So 3x completely dominates your numerator. That's also why it's called the leading term, but you can also think about it in terms of the dominating term. And what dominates in the denominator is x. So in other words, if you replace x by a million and 2, well, the 2 is almost insignificant compared to x. So really what dominates at the top and at the bottom is the 3x and x. So this is almost the same, almost, relatively speaking, to 3x over x, which simplifies to 3. So this is how you can guess that, or figure out that when x goes to infinity, y goes to 3, and when x goes to minus infinity, y goes to 3 again. Okay. So whenever you have a rational function, you can actually compare the leading terms, okay, at the top and at the bottom, simplify them if they have like common powers of x, and And then you can use the expression you get to analyze the end behavior of your function.